Right, so our last section for this week will be 3.5. Okay, we'll kind of look at two things here. First, we'll do a review of complex numbers, and then we'll apply using complex numbers to find roots. Okay, so this is just a reminder. We've said this almost every day this week, that if you have a number that's a zero of a function, that means you plug it in to the function, and the answer is 0. Right? It means that that's where the graph crosses the x-axis. Okay? It also means the number is a root. It means x minus the number is a what? If c is a root, x minus c is a factor. Yep. Right? It means all of those things. But I want to focus on the one that if c is a 0 or a root, it means that's where it crosses the x-axis. If you have a polynomial that doesn't cross the x-axis, that means you have no real roots. Okay? You always have as many answers to the problem as the highest exponent. Always. That never changes. But sometimes the answers could be real, sometimes they could be imaginary. And also, just to clarify this, if you get a repeated root, that is a second answer. Even though it's the same, that does count as a second answer. Okay, so the answers don't have to be distinct. All right, so let's take a look at this equation. Okay, this is a parabola shifted up 1 unit from the origin. Here's your normal parabola. If you were to type y equals x squared in the calculator, that's what you'd get. And this is what y equals x squared plus 1 looks like. Is that parabola ever going to cross the x-axis? No. So parabolas come from quadratics. What's the exponent in a quadratic equation? 2. So there are 2 answers to this problem. But since it never crosses the x-axis, the answers must be imaginary. Okay, let's see how that would kind of work out when we start to solve a problem. First thing I would do is move the 1 to the other side. Okay, I'm going to set it up like this. So remember, we're trying to solve for the root. So set it equal to 0. Now move the 1 to the other side. And how would I get x by itself? I'd take the square root. Square root. Square and square root cancel each other out. And I end up with x equals the square root of negative 1. Well, if we're using real numbers, can we take the square root of a negative? No. Okay, so that's where imaginary numbers come in. Okay, what I just had, the square root of negative 1, that's the most basic imaginary number you can have. Square root of negative 1, and we define that to be I. I can't prove to you why it's I, it just is. Okay, it's kind of like when you took geometry and you say parallel lines don't cross. You can't prove that. It's just, that's a definition. You just say parallel lines don't cross, and that's how you define it. Same thing with this. Okay, we just say that I equals square root of negative 1. Now from there, we can figure out what I squared is. Okay, I squared comes up a lot. So I is the square root of negative 1. So I could write it like this. It's the square root of negative 1 squared. Well, what happens when you square and square root? They cancel out, and you're just left with what's under the root. So what is I squared? What number? It's negative 1. And that's important because anytime you're left with I squared in a problem, you shouldn't leave it. I squared should always be changed to negative 1. And by doing that, you can then usually combine it with other numbers that are already in the problem. Okay, so never leave I squared in your final answer. So watch what happens if we plug I into the equation we just had. Okay, we get y equals I squared plus 1. What did we just say I squared is? Negative 1. Yeah, and negative 1 plus 1 gives me 0. So that proves that I is a root of that equation. It's one of the two things you can plug in that gives you 0. Right? But there has to be a second thing, because the exponent is a 2. We'll talk about what the other answer would be in a little bit. But I is one of the answers. Okay, questions on that? So that's how you're going to see imaginary numbers come up. Okay, so now we'll do a quick review of complex numbers and how we add, subtract, multiply, and divide them. Okay, so remember, when you write a complex number, this is how you write it. Real part first, imaginary part second. Okay, the real part is A. The imaginary part is just the B. Okay, not the I. The I is there to tell you what's in front of it, is the imaginary part. Okay, so these are all examples of imaginary numbers. Okay, 2 plus 3i, real part's 2. Imaginary part is 3. 2/5 minus I, real part is 2/5. Imaginary part, well, there's no number in front of the I, but what's invisible that's there? A -1. The imaginary part is -1. Okay, how about 3i? What's the real part there?
-3.
No, not -3.
There is no real part.
There is no real part, so what would it be? It would be what?
0.
Yeah, it would be 0. Right? You could think of 3i as 0 plus 3i. No real part, imaginary part of 3. How about -7i? What's the real part? No, because there's an I next to it. So that's not the real part.
0.
0. Right? It's the same as this one. Okay? Think of it as 0 minus 7i. The real part is 0. Imaginary part is -7. How about 4? What's the real part? 4. What's the imaginary part?
There is none.
So it would be 0. Think of it as 4 plus 0i. Okay? Usually when one of the parts is 0, we don't write it. Okay? So any questions on how you write a complex number? Always put it in this order. Real, then imaginary. Okay, so remember when we talk about I, in math, I is not a letter. I represents a number. Okay? It's the same concept as when you use this. Technically, yes, that is a Greek letter, but in math, it stands for the number 3.14. Okay? I is technically an English letter, but in math, it stands for the square root of -1. Okay, so it's a number. But when you're combining like terms, if you did something like 2i plus 3i, you can think of doing that just like 2x plus 3x. Same idea. 2x plus 3x is 5x. 2i plus 3i, that would be 5i. Okay, so think of it as a letter when you're combining like terms, but understand it's really not.
What if you have the negative of different numbers, like the negative root of different numbers? Like if I is only equal to the root of -1, right? What if you have different numbers?
Like something like the square root of -7?
Yeah.
Yeah, we'll get to that. That's a good question, though. That's why I'm going to teach it. Whenever you FOIL, okay, or whenever you multiply, you have to use FOIL. Okay, so just to kind of jump ahead and show you what a multiplication problem looks like, it looks like this. Okay, and you end up FOILing. But what happens, especially in the last FOIL, is you have a 3i times another I. So that's going to give you an I squared. So remember, anytime you get I squared, you always have to change that to a -1. Okay, so that's usually when I squared comes up. When we divide, we're not really going to do it as a division problem. We're going to do it as a multiplication problem. Okay, that's how you do complex arithmetic division. Okay, and when you multiply, you use something called the conjugate. So when we get to division, I'll show you what the conjugate is and how you do it. And now we'll look at some examples with square roots. All right, so obviously, as Luke just said, you can have the square root of negative, and you can have other numbers besides 1. You can have any number you want. Well, first thing you can do is you can split that up. Okay? Remember, there's an invisible 1 right there. Okay? So when you have a multiplication under a root, I can separate it into 2 sets of parentheses, and then I can even go a step further and separate it into 2 different roots. Okay, this only works if you're multiplying. Okay? So I have negative 1 times x, and I broke it apart into 2 different roots. Okay. Square root of negative 1, square root of x. What did we just say the square root of negative 1 is? I, and you're left with square root x. So basically, what happens is every time you take the square root of a negative, all you have to do is take the square root of your number and put an I in the front. Okay? So that negative right there basically comes out as an I. All right, so we'll try a couple examples. Okay, and I'll talk about where you put the I, because before I put the I after the number, like 3 and then an I. There's a reason why I'm leaving the I in front of the square root. Okay, and it has to do with somebody reading the problem and your answer being clear. Okay? When we go through an example, you'll probably see why. Let's try the square root of negative 7. So you can break it up just like I did up above. It's the square root of negative 1 times the square root of 7. And what's the square root of negative 1? I. And what else do I have? Square root of 7. Now, that's the final answer. Does anybody know why I'm leaving the I in front and I'm not putting it after? Denver?
You don't want to take the square root of an I.
Right. To me, this looks confusing. Should the I be under the root? Is it outside the root? I can't really tell. If you just take the I and leave it in front, that's not a question. Okay? So anytime you have a root left in the problem, just leave the I in front. Now, when you've got something that is going to simplify nicely, well, I'll show you how we can write this. Okay, so we have a square root and we have a negative underneath it. So that negative is going to come out as a what? It's going to come out as an I. And what about the square root of 4? Can I simplify it?
Yes.
I can simplify it to 2. So this time, it's okay with me if you want to put the I after it. We normally don't do this, I2. We normally write 2I. Okay. There's no confusion there. How about square root of negative 9? Yep, the I comes out, and then what's the square root of 9? 3. Since I can simplify it, I'll put it in front. And lastly, let's do the square root of negative 20. Okay, the negative comes out as a I, and what's left? Square root of 20. Now, what about the square root of 20?
You can simplify.
Yeah, how can you break up the number 20?
4 and 5.
You can multiply 4 times 5. And what's the square root of 4? 2. And then an I. Square root 5. And again, it's okay to put the I after the 2. Don't put it after the root. If you wrote I2 square root 5, I wouldn't mark it wrong. It's just not normally how we write it. Okay, so that's simplifying square roots. Same thing as with positives, except you have an I. It's the only difference.
I was gonna ask if you need an I on both of the square roots.
Nope, because that negative, it just, there's only one negative there. So you just, one negative, take out one I. Yep, not two I's. If you had something like this, you could do something different, but you'd never have two negatives under a root. I wouldn't do something like that. Okay, any other questions on? All right, so we'll go through one example of add, subtract, multiply, and divide, and then we'll apply this to the actual stuff we're really. All right, when you add and subtract complex numbers, you basically combine like terms. You can combine real part with real parts, imaginary with imaginary. All right, so Ian, what's my real part of the first number?
Real part is 7.
7? And what's the real part in the second parentheses?
4.
And what do you get if you do 7 plus 4?
7 plus 4 or 7 times 4?
Plus.
Okay. You would get 11.
Yep, 11. All right, and now we're going to combine the imaginary parts. So Nick, what's the imaginary part in the first parenthesis?
Negative 3i.
Yep, well, yeah, negative 3. And in the second parenthesis?
5i.
And what do you get if you combine negative 3i plus 5i?
2i.
2i. And that's your answer. Any questions on that? So adding, very simple. Just combine real with real, imaginary with imaginary. Subtracting, same thing. Only difference that some people forget is when you have a minus, it's like it's distributed. Okay? A lot of the mistake people usually make is they forget to subtract both of these. So in the real one, the first part is 4. In the second one, it's 6. I'm doing 4 minus 6. What's 4 minus 6? Negative 2. And now the imaginary part, it's negative 2i minus I. Okay, what's negative 2i minus I? Minus 3i. Okay, if you think you're going to forget to distribute that negative, then do it out like this. 4 minus 2i minus 6 minus I. Rewrite it so that it's distributed out like I did up above. And now combine 4 with negative 6 and negative 2i with negative I. Questions on adding or subtracting? Okay, let's look at multiplying. Okay, I already explained to you how you do it. If you remember FOIL, or some people call it double distributive, that's how you do it. Okay, I squared is going to pop up here, so we have to remember to deal with that too. So FOIL says first thing we do is 2 times 5, which will give me how much? 10? And then what's 2 times negative I? Negative 2i. 5 times 3i? 15i. And now let's look at the last one in a couple steps. What's a positive times a negative? Negative. 3i times I. 3i squared. Okay, so don't forget, positive times negative, that's a negative. 3i times I, 3i squared. All right. Anything I can combine for like terms here? Yeah?
Minus 2i and 15i.
Yep. What's minus 2i plus 15i? 13i. And now this last part, what is I squared? What number? Negative 1. So I'm going to change I squared to negative 1. And what's going to happen here? What's negative 3 times negative 1? Positive. Okay, so those two negatives cancel out and it turns into a plus 3. But now I have a plus 3 and a plus 10.
Yeah, you combine them.
And I can combine them. So what's 10 plus 3? 13. In this case, just a coincidence that the real and imaginary parts came out the same. Okay, we're going to do multiplication again when we do division. And that's the last thing I'm going to review, and then we'll start looking at roots. Okay, any questions on multiplication?
Where did you get that? Like, what's that +1 next to in parentheses?
So that's what, so I squared was a -1,
Okay.
and I had a negative from the I squared and a negative in front of the 3, so they cancel each other out.
So, but you don't add that +1 to it?
No, because it's multiplication. It's positive 3 times.
Oh, okay.
So what's going to happen is this.
Oh, so that's just a positive one.
It's just, yeah, so it's -3 times -1,
Yeah.
which turns into positive 3. Okay? Or some people, when they see a negative and an I squared, they just cross out the I squared and make that a positive, because they know I squared is -1. Could do it that way too. Any other questions on that one? All right, so the last one we're going to look at is division. But to do division, I said earlier, we have to use something called a conjugate. To find a conjugate, okay, all you really have to do, I wrote the word negate the imaginary part. Okay, negate just means change the sign. Okay, so take the sign and make it the opposite of what it is now. Okay, just on the imaginary part. Okay, so if you have a number and you do that, change the sign of the imaginary part, that's called the conjugate. So let's say I had 3 plus 2i. Anyone think they could tell me what the conjugate of 3 plus 2i is? Nick?
3 minus 2i?
Yeah, it's 3 minus 2i. How about if I had 4 minus 5i? What would be the conjugate of 4 minus 5i?
4 plus 3, 5i.
Yep, it'd be 4 plus 5i. How about if I had 3i? What's the conjugate of 3i? Negative 3i. If you're confused here, put the real part. It's 0. 0 plus 3i, the conjugate is 0 minus 3i. And how about the conjugate of 6?
6.
Yes, it stays the same. Again, if you're confused, put the imaginary part. 6 plus 0i, the conjugate is 6 minus 0i. But plus 0 minus 0, it doesn't change it. Okay. So any questions on, if you're given a number, how you find the conjugate? All right. So now we can use that to do division. So the problem with, the only problem with really division here is you're not allowed to leave I in the denominator. Somehow you have to get rid of the i's in the bottom. And if you use the conjugate and do what I'm explaining right here, it'll take care of all the i's in the bottom. They'll all disappear. Okay, so to divide two complex numbers, you're going to multiply the numerator and the denominator by the conjugate of what's in the bottom. Okay, so the first thing is you're going to find the denominator, which that should be pretty easy. Then find the conjugate of it. And then multiply the top and the bottom by the conjugate. Okay, so I've got 2 minus 3i as my denominator. What's the conjugate of 2 minus 3i?
2 plus 3i.
2 plus 3i. So I'm going to multiply top and bottom by 2 plus 3i. Okay, before I do this out, any questions on how I got what I have right here? Okay, so so let's do it out. 5 times 2 gives me 10. What's 5 times 3i?
15I.
2 times I? So what's 15i and 2i? 17i. Okay, there's no I squareds here because we haven't multiplied an I times an I yet. You get a 5 times 3i, which is 15i. 2 times I is 2i. And then I added them together. And when you add like terms, you don't get an I squared either. The only thing that's going to give me an I squared is the last one. So I have a positive I times a positive 3i. So that's positive what? Positive 3i squared. Now watch what happens in the bottom. You got 2 times 2. What's 2 times 3i?
6I.
What's 2 times negative 3i? Minus 6i. So really, we just wasted time doing the outer and the inner part of FOIL because it's always going to cancel when you have conjugates. Now I have negative times positive. That's a negative. 3i times 3i. 9i squared. Okay, so there's a lot of things we need to simplify. 3i squared. What number is that?
-30.
Yep. Any question on how he got that? All right. Now in the bottom, I've got plus 6i minus 6i. That's gone. 4. And what am I going to put after the 4? I have a minus 9i squared. What is that? Would be a positive 9. Right? Because I squared is negative 1. So that negative is going to cancel that negative. Okay, any questions on that? Now we almost have our final answer. What am I going to end up with in the top?
7 plus 17.
7 plus 17i. And in the bottom? 13. Now, the only problem with that answer is I told you when you write a complex number, you're supposed to have real part, then something like a plus or minus, and then imaginary part. Right now, you've got one big fraction. Okay, to split this into 2 parts, it's very, very simple. Take the real part, put it over 13, copy down your sign if it's plus or minus, and then take the imaginary part and put it over 13. And then just put an I next to it. Right, so all I did was 7 over 13 plus 17 over 13. I. Okay. Most of the time in the book or on a test, you would not see a multiple choice answer listed in the second to last step. You'd see it listed like the last step. So you need to understand those two are the same. Okay, and that's the review of complex numbers. Okay, so any questions on that?
So how did you get rid of the 9i to the second on the bottom?
So we had 4 plus 9, or it was 4 minus 9i to the second. So it's 4 minus 9, and I squared is what number?
-1.
Negative 1. And now what's negative 9 times negative 1?
Plus 9.
Plus 9. So just multiply those together, and that's your denominator. Okay. So any other questions on division? All right. So now let's find some roots. Okay. So we're going to do the same exact things we did yesterday. You can use rational root theorem. You can use the graphing calculator. We're going to use synthetic division. Everything I just said works exactly the same way with complex numbers, except now you might get answers that have I. All right, so let's solve this polynomial. I'm already writing A, B, and C to set it up for quadratic formula because I'm looking at it quickly and I can tell I'm not going to find two numbers that help me factor it. Two numbers that multiply to give me 1 and add to give me 1. It's not going to work. So when I start to plug into the formula, what's A?
1.
B?
1.
C? 1. Okay, so let's fill in our quadratic formula and see what we get. How does the quadratic formula start?
Minus B
Negative B. Yep.
plus or minus the square root of B to the second.
Yep.
Minus 4
Plus
Yep. Minus 4
times A and C
times A times C
divided by 2.
divided by 2A, which A is 1, so 1 times 2. 1 times 2 is 2. Okay, so we get negative 1 plus or minus the square root of, I just did 4 times 1 times 1. Okay, I'm probably showing out more steps than you really need to, but I'm just trying to show you every step. What's the square root of, what's 1 minus 4? Negative 3. And earlier I showed you how to deal with the square root of negative 3. How do we write that? I square roots of 3. Now this is just like the last problem we did with the division. You don't really have a real part and an imaginary part separate. You've got one big fraction. So on a test, the answer would be almost written like this, except you'd have to separate it out. What's your real part here?
Negative 1 over 2.
Yep, negative 1 over 2, plus or minus. And what number is with the I? Square root of 3. And that's also going to be divided by 2. It's exactly what I just did in the last problem, to split it into real part, imaginary part. And those are your two answers. Now, if I write these two numbers out, what's the relationship between them? Negative 1/2 plus root 3 over 2i, and negative 1/2 minus root 3 over 2i. What's the connection? There's a name when you do what I just did right there. What are they? These are conjugates. Okay? So in example 4, the two roots that you just got are conjugates. In fact, that will always happen. Okay? Complex roots always occur in pairs. You could never solve a problem and get one complex answer. You can get 2, 4, 6, but you can't get an odd amount. Okay, so complex roots always occur in pairs. Specifically, they occur in conjugate pairs. So if you were solving a problem on the test and you figured out 2 plus I is a root, well, I guarantee you 2 minus I has to be a root. That's what's kind of nice about complex answers. If you find 1, you really find 2. Okay, they always occur in conjugate pairs. Okay, unless you don't have an imaginary part. If the imaginary part is 0, well, then that's just a real answer, and that's what we talked about yesterday. So everything we've already done. Factor theorem, synthetic division, rational root theorem, all the theorems, they all work with complex numbers. Okay, so the first thing I'm going to do is I'm going to show you how to do synthetic division with a complex number. It's exactly the same process. It's a little bit more arithmetic. There's more, when you multiply, it's not as easy as multiplying regular numbers, because when you multiply with imaginaries, you need to FOIL. Okay? But I wouldn't give you anything on the test above a cubic, so that automatically limits how many times you have to do synthetic division. If you had like a exponent of 4 or 5 with an imaginary, that's going to take a little while to do. But cubed isn't too bad. It's not as easy as a quadratic, but not as bad as it could be. Okay. Does everybody have up to the b not equal to 0? Okay. So if you want to show something as a root, you put that on the outside of the bracket. And now write down your coefficients. What are my coefficients going to be here?
x3, I mean 1, 0, 1, and 10.
Perfect. Yeah, you don't want to forget that 0. Hey, now when I do synthetic division, what's the first thing I do? Yep, bring down the first number. Okay, that's pretty easy. Now I'm going to multiply 1 minus 2i times 1. Okay, it's kind of like doing this. You need to distribute it. But since I'm just multiplying by 1, is it going to change it? No, that probably won't happen again. Maybe, we'll see. So multiply it, and then put your answer in the second column, and now add. What's 1 minus 2i plus 0?
1 minus 2.
Stays the same. Okay, now here's where the arithmetic gets a little more involved, but luckily we're only going to have to do it twice and then we're done. We have to multiply 1 minus 2i times 1 minus 2i. So I'm going to do it off to the side because I don't have the room where I'm doing the division. So 1 minus 2i times 1 minus 2i. Okay, what's 1 times 1? 1. 1 times negative 2i.
Negative 2i.
And then I have another 1 times negative 2i. So that's a negative 2i, and a negative 2i is negative 4i. Negative 2i times negative 2i.
4i squared.
Yep, positive 4i squared,
Just be minus 4.
which is really minus 4. And now, what's 1 minus 4?
Negative 3.
Negative 3 minus 4i. Now add. What's negative 3 minus 4i plus 1?
2 minus 4i.
-2.
Negative 2. You're never going to have an imaginary number to add, but you're always going to have to add the real parts. 1 plus negative 3 is negative 2. And now we're at the last step. Okay. And I'm trying to show that this is a root. So what am I hoping I get a remainder of? 0. So what am I hoping this number comes out to right here? I'm hoping I get negative 10. So somehow all the i's should disappear at this step. Okay, we'll see. So I have 1 minus 2i times negative 2 minus 4i. Remember, we're hoping for negative 10. Okay, what's 1 times negative 2? 1 times negative 4i.
Negative 4i.
What's negative 2 times negative 2i?
4i.
Positive 4i. And then negative 2i times negative 4i.
Positive 8i squared.
Yep, it's a positive 8i squared.
Just be minus 8i.
Negative 4i plus 4i. And I think, Luke, did you say that? What?
It would just be minus 8.
It would just be a minus 8. And what's negative 2 minus 8?
Negative 10.
There's my negative 10. Okay. So it is a little bit more work, but it's not too bad, especially the last one and the first one. Those aren't bad. Just the two in the middle that take a little extra time. Okay, so any questions on that?
How would I write that out?
Oh, that's it. So just show that that's a root. I guess you could say, so since I have a remainder of 0, 1 minus 2i is a root.
So if you had to write it off,
Just like that. You would never write the quotient out.
oh, you went.
No. we wouldn't be writing the quotient out here. This is all you'd have to write. Since I have a remainder of 0, 1 minus 2i is a root. 1 minus 2i is a 0. Is 1 minus 2i an x-intercept? No. Normally the root is an x-intercept, but not when it's imaginary. So the last thing I want to ask, and you're going to see something like this on the test, start with a regular number. If 3 is a root, what's a factor? X minus 3. What if 9 is a root?
X minus 9.
X minus 9. Always x minus your root is a factor. So now, 1 minus 2i is a root. What is a factor?
X plus 1 minus, X minus 1 minus 2i.
Yes. If 1 minus 2i is a root, x minus that is a factor. Now, do complex numbers, when you get a root, what always has to happen? 1 minus 2i is a root in this problem. What else is automatically a root? Yeah?
So because 1 minus 2i is a root, then you're going to have 1 plus 2i is equal to
Yes. Even if they don't say that, it has to be true. Okay? If 1 minus 2i is a root, 1 plus 2i is a root. Now, last question on this one. If 1 plus 2i is a root, what is a factor?
X minus 1 plus 2i.
Yes. It's always x minus your root is a factor. Now, I'm not going to do this out. I'd have to distribute the negative and write x minus 1 plus 2i, x minus 1 minus 2i. And if you were to multiply all that out, you would get a very nice answer. It turns out, when you multiply things like this out, all the i's just disappear. So it's going to be kind of weird in the middle. You're going to have all these weird terms, but they're all going to disappear. And you're going to end up with something like x squared plus 3x plus 6. Okay, I don't know exactly what it comes out to, but it's something like that. Okay, and we'll go through one where you do this out. I think there's one in the homework. If not, we'll do one before the test because this is on the test. Okay, so I extended this problem a little bit here just so you could see something that's going to be kind of like what's in the test. But remember, all you really had to do was the synthetic division here. Okay, but I don't want to continue that any further.
With the two factors, but are they factors by themselves, or do you have to multiply them? Like, FOIL them, or?
Well, it's kind of like saying, if 3 is a root, x minus 3 is a factor, and if 2 is a root, x minus 2 is a factor. Do you have to FOIL that out to write the answer? They probably would on the test. You'd probably see this. That's probably how they would write it. So yeah, usually you have to FOIL it out. So it's a little messier foiling out something like this, but the answer comes out just as nice when you're done. Okay, and I will do one either before the test or from the homework. Okay. How come an odd degree polynomial always has to cross the x-axis at least once? It's not true for even degree, but why do odd degrees always have a real 0? Guaranteed. Well, what do odd degree polynomials always look like? Like if you were to graph x cubed. Tell me what the end behavior looks like. Yep.
It'd be always going up. Like if it was x cubed, it would have like up to 3 terms, right?
Okay, it could have up to 3 terms in the middle, but what's going to happen on the ends of it? Like,
it's going to reverse direction.
Right, one end is always going, it does some stuff in the middle, right? One end is always going up, one end is always going down, and it's connected. right? Polynomials, you never pick your pencil up. So if you go down forever and you go up forever without picking up your pencil, are you going to cross 0 at some point?
Yes.
Yes. Okay. Now with a parabola, the behavior could be up on the right, up on the left. Do you necessarily cross the x-axis with a parabola? No. Okay, so any even degree polynomial has either up and up behavior or down and down. But odds, I guarantee you'll cross the x-axis at least once. All right, so let's try to find, let's see, we have a couple left. Let's try to find the roots of this equation. 0 equals x cubed minus 1. Now, why can't I just use the quadratic formula on this and get the answers? It's cubed. It's not a quadratic. But we can turn it into a quadratic, just like we did yesterday. Okay, the way you turn it into a quadratic, what theorem do I have to use first, and then use my graphing calculator? Yeah, use the rational root theorem. Find a root, confirm it's a root using your calculator, and then divide through synthetically by it. Once we do that, we'll turn the cubic into a quadratic, and then from there we can solve it. Okay, but I have to be able to find a rational root. If I can't, I'm done. There's nothing else I can do with this problem. So let's make a list of rational roots, and then use the calculator. What could be my values for p here? My values for q. Also plus or minus 1. So what would be every possibility I could have
1.
for p over q? Plus or minus 1. So when I graph this, it has to cross the x-axis at 1 or negative 1. Otherwise, I couldn't ask you to solve it. Okay, so it's x cubed minus 1. I'm zoomed in a little bit, but that's fine. So where does it look like it crosses? So the candidate in this case, if I asked you to make that list, the candidate would be plus 1. I'm going to confirm it right now. It is 1. But what I'm really interested in is when I do the synthetic division, I know I'm going to get a remainder of what? 0, but I really want the quotient, because the quotient is going to give me the other two answers. And since I'm only seeing the graph cross once, the other two answers are probably imaginary. Perfect. Okay, so that's kind of the thought process when you go through it. So let's divide through by 1. My coefficients are 1, 0, 0, negative 1. Bring down the 1. 1 times 1. 0 plus 1. 1 times 1. 0 plus 1. And 1 times 1. 1. And this is pre-calculus. And negative 1 plus 1. 0. I already knew that that was going to be the remainder. This is my quadratic. A is 1, B is 1, C is 1. Didn't we already solve that? Yeah. So if I didn't have the work, I would have to do that out. But here's the work. A is 1, B is 1, C is 1. These are my other two answers. Negative a half plus root 3 over 2i and minus root 3 over 2i. So let's list our roots. Negative a half plus or minus root 3 over 2i. Those are the imaginaries. And 1. Where did I put it? Right there. And I got that from the rational root theorem in my calculator. Right, so there's your 3 roots. 2 imaginary, 1 real. Any questions on that one? right? So this I already said to you earlier, the total number of answers you get always equals the degree of the polynomial. Okay. Degree 3, 3 answers. If you had a degree, it's another degree 3, it would have 3 answers. Degree 2, 2 answers. Degree 6, 6 answers. Degree 7? What do you think? Okay, and this theorem, the linear factorization theorem, all that basically says is that whatever the degree is, that's how many factors you have. So for example, if I gave you a cubic, you can factor it as 3 things. In this case, that's what it actually factors as. X plus 1, x plus 2, x minus 3. Okay, if I have, for example, a degree 5 polynomial, it could factor like this. But it's important to understand when I say that there are 5 answers, the 5 answers don't have to all be distinct. This problem has 5 answers. -1, -1, 2, 2, and 2. Those are the 5 answers. Okay, some people get a little confused with that and think they have to be distinct. They don't. They can repeat. Okay, and I didn't really say this term yesterday, but the proper term here, we'd say that -1 is a root, or it's a 0, and it occurs twice. So we say it's a root with multiplicity 2. Another root we have is 2. And that occurs 3 times. Okay? So we'd say 2 is a root of that polynomial with multiplicity 3. Okay? It occurs 3 times. Right, so any question on the terminology there for a repeating root? All right, so I'm not going to do this example. If we want to do another one, we can, but first I just want to make sure we kind of understand the idea of complex roots occurring in pairs. So let's say I had a cubic. How many answers are there to a cubic always? There are always 3. So I want to list kind of the scenarios between how could I have reals and imaginaries. What's one scenario that could happen with a cubic?
1 real, 2 imaginary.
Yep, I could have 1 real, 2 imaginary. That was the problem we just did. What's another scenario with a cubic?
The real one.
Can you have 2 real, 1 imaginary?
Non-positional.
Because imaginaries always have to occur in pairs. So we couldn't have 2 real, 1 imaginary.
It's all imaginaries?
Well, all imaginary for a cubic would be how many imaginaries? 3. Can you have an odd amount of imaginaries? Nope.
3 real, 0.
You could have 3 real and 0 imaginary. Now, when you say 3 real, that includes the possibility all 3 are distinct. There's 1 repeat in there, or there's no repeats. They're all real, bottom line. Let's say I had make up another one, 4th degree polynomial. What are some scenarios I could have here for roots?
2 real, 2 imaginary.
Sure, you could have 2 real, 2 imaginary.
4 and 0.
Yep, you could have 4 and 0.
Or 0 and 4.
You could have 0 and 4. Could you have 1 real, 3 imaginary? No. We already did 2. Could you have 3 real and 1 imaginary? No. So you just have to go through the list and basically go through every real number you can and make sure they add up to the degree. and the imaginary column is never odd. And that's it. Those are the scenarios. Again, this scenario includes 4 distinct roots, 4 repeated roots, every possibility you could have. All right, so anybody think they need to see another one like example 6? That would be the last one if anybody needs to see another one. We're still going to do one before the test tomorrow. So. Okay. All right, so the homework kind of jumps around a little bit like usual. It's on 193. Not every problem is finding roots. Some of them are just like write the conjugate of the numbers. It's a real fast problem. Or take these 2 numbers and add them together. Okay, really quick stuff. Some of them you have to find roots. Okay, so 1 through 3, 9 through 13, 15, 19 to 22, and 25 to 27, 32, 36, 39, and 40. Okay, some problems ask you to find how many real roots there are and how many imaginary. You don't actually have to find them. All they want to know is how many real, how many imaginary. So you just have to make a list. Okay, don't forget I will be after school today if you need extra help, and we have our test tomorrow.
Can you put up like the last